Okay, so good morning, all of you, and welcome back on the second day of the school. So the first talk will be given by Professor Carl Caves, and this is his also last talk. He also has a distinguished lecture later in the next week. So Professor Caves.
All right, let's see, is the mic working? Yep, terrific. All right, so I'm going to talk today about a thing I told you I would talk about yesterday, Fisher information and the quantum Cramer-Rao bound. This basic idea of Fisher information lies at the base of every bit of current quantum metrology. If you want to make precise statements about what's going on. Now, generalizations of it are often important, but we're going to talk about the simplest, nearly the simplest kind of Fisher information here. So, Fisher information is all set up for single parameter estimation, where it provides a bound on the mean square error in estimating a classical parameter. And that parameter is coupled to a quantum system, and the bound on the parameter is in terms of the inverse of the quantum information of the quantum Fisher information. Now, a harder topic is multi-parameter estimation, where you have a quantum system that is affected by many different parameters, and you want to know something about all of them. And in that case, you can derive a similar Fisher bound in terms of the, for the covariance matrix in estimating those parameters in terms of a matrix, a Fisher information matrix, or actually the inverse of the Fisher information matrix. Now, this is a much harder topic than this one. And the reason is kind of a lesson in quantum information theory for everybody. If somebody gives you a bound on something, first question you have to ask is, can the bound be saturated? That is there something that allows me to achieve that bound? You know, because it's very easy for me to say that I am currently bounded by, I'm above the floor, but I could go stand on this desk, and what you'd want to know is, am I actually capable of standing on the floor? So for the quantum Fisher bounds, the question is, can you achieve those bounds? And that actually means, can you achieve them given a certain measurement, quantum mechanically, or given a certain quantum state, and given a certain quantum state, quantum mechanically. That works for the single parameter estimation, and it doesn't work here, and that complicates things enormously. And more or less the reason it doesn't work is because the parameters, the several parameters you want to estimate might be coupled to observables that don't commute. And then the quantum Cramer-Rao bound or Fisher information bound ignores the fact that they don't commute, and but that keeps you from achieving the bound. So that's why we're going to stick with the single parameter estimation here, and we're also going to stick with it for the fact that if you don't know about the single parameter bound, there's little point in telling you about the multi-parameter bound. So that's the philosophy we're adopting here. All right, so I want to just review a slide that I talked about yesterday, and let's have the setting for what we want to talk about. All quantum Fisher bounds are about following. You have a parameter that's coupled to your system. It changes the density operator of a quantum system, or the probability distribution for some variable in a classical system. And the Fisher bound is aimed at saying, if I only want to detect small changes in that parameter, so I have a lock point where I'm operating in terms of that parameter, and I want to detect small changes away from that lock point, how well can I do that in terms of mean square error? That's the question that Fisher information answers. And you can see that it's really the question of distinguishing the probability distribution for something, or the density operator, at the fiducial point from a slightly changed point. So Fisher information is basically about how well can I distinguish nearby probability distributions, or how well can I distinguish neighboring density operators, where the neighboring is the parameter moves me from a fiducial point to a nearby point. Okay, so that's the question we're trying to answer. And Fisher information basically answers that question precisely, but the basic philosophy is, how well can I distinguish probability distributions? So the derivation that I gave yesterday and that I'm about to run through again is really the way Fisher would have thought about this in the 20s of the last century, when he devised the notion of Fisher information. He wouldn't have had proofs because he was thinking about Gaussian noise, but the proofs were provided by Cramer-Rao independently just after World War II in the late 40s. All right, so that's the point. We're trying to distinguish probability distributions. And how could we do that? Well, we could sample from the probability distribution many times, find a frequency for all the outcomes. And the frequency of all the outcomes is a way of estimating the probability distribution. And the Fisher information is estimating a probability distribution in terms of units that are the basic error in determining probability distributions. That is the variance in determining probability distributions. So we're going to go through this again. We're going to have a problem where we only have two outcomes. That could be polling. Let's think about it as polling, where we have two outcomes. One that's you want to vote for candidate X, and the other is you want to vote for candidate Y, and we're polling to see which one you want to do. And we'll poll n people, and little n of them will give candidate that corresponds to probability P. And so the frequency for that is a number, n divided by n, and its mean value is the probability for that outcome. Okay, and we're trying to estimate that probability. That's what we're trying to do. The variance in that frequency is just given by this famous formula PQ over N, where Q is 1 minus P. So it's the probability for the other outcome. All right. So Fisher information measures the distance between neighboring probability distributions in units of their distinguishability. So if we have two distributions whose have different P's that are different by a tiny amount, delta P, we measure how well we can determine delta P in terms of the variance of our estimate of P. That's what we mean by statistical distinguishability. We just rewrite that. There's a slight cleverness involved in rewriting it this way, because this is the way it looks with the Fisher information. There's an n out in front for the number of trials, and that is part of the Fisher information. That's just the 1 over square root of n improvement in sensitivity as we poll more and more people. And then this is the Fisher information. So take a moment to stare at that. And let me ask, do I actually have till 10:30? What, I'm gonna have to talk very slow, but I'm sure I can take up the time. I'll just try to explain things better. All right. So that's the Fisher information, and it has a form which, you know, you should look at it and see this is an important form. It's this difference between probability squared divided by the probability plus the other difference in probabilities divided by by its probability. These two delta p squareds and delta q squared are the same because p is 1 minus q. But that won't be true if we have more than two outcomes. Anyway, the important point is this is not any of these things, which you might write down immediately. For instance, this one you might think, oh, this is a terrific way of talking about the distance between probability distributions. This is just the Euclidean metric on the probability simplex, that is the space of probability distributions. And it's not the right answer. Nor is this the right answer, or well, you probably can guess that if you're going to have something that's smooth, you're not going to have absolute values in it. But anyway, and I just want to make this point again. So the probability simplex in this case is very simple. It's just a line running from q equal 1 to p equal 1 in a two-dimensional space. In higher dimensions, the simplex is always something like that. And for 3 outcomes, it's a triangle. For 4 outcomes, it's a tetrahedron. It's always a regular whatever hedron in arbitrary dimensions. And if you do the following, so this metric, the Fisher information, is not the standard metric that you would have for this if you induced a metric from the surrounding 2 space. This is the metric you'd have if you went from the surrounding 2 space. But if we introduce these square root quantities, square root of p, square root of q, then this thing pops out to be a little piece of a circle, and then the Fisher information is just the Euclidean metric, the induced metric from the Euclidean metric on the outside. So the metric on there is the natural metric on that piece of a circle, and in higher dimensions, it's a piece of a big sphere of arbitrary dimensions. Now, I point this out at some risk because the minute you point this out, what do you think of when you see square roots of probabilities? Quantum mechanics. God, that has to have something to do with quantum mechanics. And there's all kinds of things like that in quantum information theory where square roots of density operators are important. But the reason I do this with some trepidation is if you go down that path, well, bye-bye, see you later. You'll never come back. And it's not a good path to go down, to think that that somehow is fundamentally connected to quantum mechanics. All right. So now here's the general Fisher information for a bunch of, for a parameter. So we now have a parameter phi that affects a probability distribution pj of phi in the way we just said. So now delta pj will be the derivative of pj with respect to phi times delta phi. And the Fisher information, that's what we just wrote down, looks like just the sum over the alternatives, that is the things we're actually sampling, times the square of this derivative. And as I just said, there's actually a delta phi squared, which should be then will be on this side of the equation. But anyway, this is just a little change in perspective. This is going from parameter estimation, from thinking in terms of distinguishing probabilities to thinking in terms of parameters. And here's a very important formula. If we just write this derivative as the derivative of a logarithm, we can now write this as the mean value of this squared logarithmic derivative, okay? And that's the thing that comes up all the time. Very important for reasons that we'll see as we go along. So what should I say here? This logarithm is probably the reason that this got, no, God, it's hard to say how I got the name information in it. Somebody asked me yesterday why it was called information, and I said, because the people who named it didn't know what they were doing. It's a terrible name. It should be called the statistical distinguishability. It should not be called information at all. The only connection it has with information is that if you look at relative entropies, which is the entropy sort of relative to a particular point, either in a simplex or in density operator space, the Fisher information is the expansion of that to nearby density operators or distributions. It's expansion of that relative entropy, and entropy is connected to information. All right. Apologies to all those people who love the name Fisher information, but I think it's terrible. All right, now, as I told you yesterday, this is going to be a real lecture because we're actually going to prove the Fisher bound, and we're not going to prove it in the most trivial form that which we could do. This could be a mistake, of course, but then I certainly wouldn't use my 90 minutes if I proved it in the most trivial way. So we're going to prove it in a way where we actually show something interesting. So what we have is a system. There is a parameter gamma that we want to estimate. It generates parameter displacements with a conjugate actual operator H. So there's a Hamiltonian that has a gamma H in it. And because I perhaps stupidly didn't set H bar equal to 1, H bar is in there as well. So what anybody would say is gamma is the parameter conjugate to the Hamiltonian little h. Now we're also going to allow another Hamiltonian that doesn't depend on gamma. And that other Hamiltonian can depend is not only a Hamiltonian for the system, but could involve any other systems that are around as well. Those systems are coupled to our primary system, but they don't see the parameter directly, okay? And so the picture is sort of this. Here's our system, here called a probe, and here's the other systems, and we allow them to interact. And then we can allow any measurements we want and with feedback. So these are so-called controlled gates where we feed back measurement results from one system to the next. By the so-called principle of deferred measurement, we can push all the measurements to the end. And here's our Hamiltonian involving the system and the ancillary and all kinds of other stuff that's going on that is where there's feedback from the ancillary to the system. And then we make our measurements in the end. So a key point, of course, is going to be classically, you say what your sample space is, that is what you are in some sense measuring. And quantum mechanically, well, there's a lot of measurements you could use. And the Fisher information is surprisingly going to answer the question of what's the best measurement to make when we impose a parameter in this way. All right, so that's the picture. We have a system, we have other systems. They all have this big Hamiltonian, but only the system sees the parameter, and that is imposed by this Hamiltonian little h. All right, so now we'll write down some stuff. We're going to say the initial state of everything. We're going to call that row 0. There's going to be a lot of times in this. Things are going to evolve in time, and we're going to call the final time t when we're actually going to ask how well can we estimate things. We're going to call that little t. And intermediate times we're going to label by s. The evolution operator that goes with the Hamiltonian, we're going to call u sub gamma of s. And there's going to be an estimator POVM e gamma sub s. So I'll come back to that in a second because I have a feeling like that's where I'm going to, place where I'm going to get into trouble. So here's our system, has initial state, evolves under the von Neumann equation according to this. So the evolution operator acts on both sides to give us an evolved state, which depends on gamma at time t. This evolution operator satisfies the kind of state-independent Schrodinger equation, like any good evolution operator does. Then we say the following: no matter what estimator we choose for estimating our parameter, that's just a question of processing some data. And when we process that data, we can always encode our estimator of gamma in a so-called POVM. So let me ask, how many people here are familiar with POVMs? Positive operator value measures. Give us how many people are totally comfortable with POVMs? Yeah. No. Well, this talk is for you. But so it looks like I better say what a POVM is. Regrettably, I will tell you next Wednesday at 4 p.m. when I give my other talk, but that'll be a little late. Although I think it must be that Saha is going to say something about POVMs this time. Did he say something about POVMs yesterday? You'll get to POVMs. Okay. So POVMs are positive operators. That means they're operators that have no negative eigenvalues. They're Hermitian and they have no negative eigenvalues. And they are the generalization of the projection operators of von Neumann measurements. And they satisfy a completeness property, just like the projectors of a von Neumann measurement. If we integrate over all the results, in this case, the value of the estimator, we get the identity operator. And it turns out that's the only properties you need to generate probabilities in quantum mechanics, is to have a Hermitian positive operator that sums to 1. And then you can generate probabilities from it. So it corresponds to a measurement. There's a bunch of formal stuff you can go through to show that that's true, but if you just start from ground zero and say, what property do the operators from which we extract probabilities of measurement results have to have? It is the properties of POVMs, positive operators that sum to 1. Okay? Everybody sort of comfortable with that? Because God, if you're not comfortable with that, we're gonna, oh well, there's nothing we can do at this point. All right. So the point here is for me to run on enough so that you can look at these equations and start to see what the structure is. This is the way we extract a probability from a POVM. And here we have labeled the POVM by the value of the estimator of our parameter. And we can always do that. That's a thing you can easily show. And so we generate probabilities by taking the POVM element for a particular gamma est, multiplying it by rho gamma t and taking a trace, and that generates a probability for us. You can see that this property, if we integrate over gamma est, the fact that this thing integrates to 1, and then the trace of rho gamma is 1, means that we, regardless of what rho gamma is, we generate a probability distribution. And that's really all you need to be off and running. You just have to trust me if you don't believe that. All right. So any questions at this point? This is the picture. All right. Now we're going to do some stuff. So we're going to say that our estimator is, here's the value of the estimator, and we're going to subtract off its mean value, calculated using that probability that we just wrote down, okay? An unbiased estimator is one for which the estimator is equal, the mean value of the estimator is equal to the actual value of the parameter, and the derivative of the estimator is equal to 1. You would say this follows from that, but these conditions can be imposed locally at the fiducial point, and then it's called the locally unbiased estimator, and that's all we actually need for this. But you don't need to worry too much about that distinction because we're not, we can just assume we have this at all gamma. All right, so now we're going to define the following quantity. We have our estimator, and we're going to want to define a quantity which is sort of the deviation of that estimator from the true value of the parameter, well, which we're going to call delta gamma. The first thing we have to do is the estimator could be running along, could have different units in some sense than the true parameter, or it could have a steeper slope than gamma. So to convert, we divide by this derivative. And then we subtract off the true value of the parameter. And you can just see if we plug this in, this looks like this. So it's the deviation of the estimator from its mean plus the mean value of this quantity, the mean value of the difference between the parameter and its true value. Okay? So now we have, so I forgot, let's back up a step. You know, I gave you this kind of touchy-feely derivation of the Fisher information, which is the way Fisher thought about it. But now we're going to show you a proof of the Fisher bound. And what you will notice is in the proof, you don't appear to be heading in the right direction at all. And of course, this is the problem with most proofs, right? You head off in some direction that Cramer and Rao had the genius to figure out. It's not very hard, actually, but they had the genius to figure out to head in that direction. Even though when you start, it doesn't look like you're heading in the right direction at all. In some sense, this is what mathematics or theoretical physics is about, is thinking up new ways to think about things, which are not the naive way of thinking about them, and then proving something as a consequence, or having rigorous consequences of what you're doing. So we're going to write down here the normalization of this probability and the mean value of gamma est, which is the quantity that appears here. So that's just integrate over this probably, integrate gamma est over that probability. All right, so everybody would agree with those two statements, right? Those are definitely true, right? It's just a statement of what 1 is equal to and what the mean value of gamma est is equal to. And then we do the following. And this is the kind of genius part of the proof. It's all here. And so we're going to take the derivative of this quantity with respect to gamma. So notice it's a function of gamma through the dependence of this probability distribution on gamma. So this first term here is literally the derivative of this. So we take the derivative of that probability with respect to gamma and multiply by gamma est and integrate. And that's clearly the derivative. Why do I have this in here? Well, it turns out to be convenient, and we can put it in there because this term is 0. How do we know that? Because this doesn't depend on gamma est. It's a mean value. It depends on gamma. It can be pulled out of the integral, and the rest of it is just the derivative of this 1, and that's 0. Okay, so very clever. Oh, we didn't mean to go there quite yet. And you can see that what we did was now we have this delta gamma est here. And now we pull our little trick of writing in things in terms of logarithms. So we write the logarithm of p. So its derivative is 1 over p. So we have to put a p here. And now this is just the mean value of delta gamma est times d log p d gamma. Okay, so the kind of correlation between delta gamma est and this funny thing, which is itself, it's self-referential. That's why it's sort of like an information. This mean value of the logarithm of a probability differentiated. Okay, so this still looks a long way from where you want to be in terms of proving something, but now we're about to show you where that goes. So here we've repeated what I just had. That is, this derivative is this mean value. And now we're going to say, any mean value is subject to the Schwarz inequality. That is to say, the mean value squared is less than, the mean value squared of a correlation is less than or equal to the correlation of the uncertainty of the variance of the first quantity times the variance of the second. That is, we average the square of delta gamma est, average the square of this d log p, and that's greater than or equal to this square, which is just this derivative, derivative squared. So it's that correlation function squared. So everybody buy that? That's the Schwarz inequality. It's a terrific inequality. The world is, my first student when I went to UNM, Chris Fuchs, now famous for cubism, he wrote his whole dissertation was just an application of the Schwarz inequality, which I tell him that and he's not happy when I tell him that, but anyway. If you don't know the Schwarz inequality, it's incredibly important. Figure it out. All right, so now what we've got is this quantity here, and now we just defined this thing to be the Fisher information, the mean value of this logarithmic derivative. And then we can just take delta gamma, which we've written here, take its average. The product in the average vanishes because delta gamma est is 0. And you can see delta gamma squared is equal to this plus this. This is greater than or equal to 1 over f of gamma plus this, and that's greater than or equal to 1 over f of gamma because this is positive. okay? So for an unbiased estimator, which I think is what this mean of delta gamma is 0, and so we will achieve, you can forget this thing in the Fisher bound, okay? So in essence, you're always going to want to use unbiased estimators. That doesn't get you to the Fisher bound, but you can see now the structure. This difference between the parameter and its true value, the mean square error in determining the parameter is greater than or equal to 1 over the Fisher. And to get that, we came through this odd thing of establishing a certain kind of correlation function that looked totally irrelevant. And that, of course, was the genius of Cramer-Rao to realize that you should do that, to put Fisher's bound, Fisher's kind of vague thinking onto a firm footing. And I often think, God, how do these people get stuff named after them for doing something so trivial? There's nothing named after me, and I've done stuff that's less trivial than this. But the answer is, it's not trivial until you do it, and then it's suddenly trivial, right? That is the answer. Everything you think is trivial was not trivial until it was done, realized and done. So, all right. So now let's just kind of repeat that. There's our Fisher information. Here's the form, we just wrote it in, and then we write it out again in terms of an actual mean, and then we convert it to that form where we take the derivative of the logarithm. And this is where we start from the Fisher style argument involving polling. And the Fisher bound is that Fisher bound, which we're going to call the classical Cramer-Rao bound, is that the variance of the variance of the deviation from the parameter is greater than or equal to 1 over the Fisher. And a thing that's been proved that I'm not going to do is the Fisher bound can be attained asymptotically in many trials. Of course, then you'll have an N in it, asymptotically in many trials using maximum likelihood estimation. And that's really the statement that in many trials, things become Gaussian and the maximum likelihood estimation is trivial. It's just picking the peak of a Gaussian, and everything's really back to Fisher's original argument involving Gaussians. It's a little more complicated than that, but that's basically what's happening. All right, any questions? Because that's the classical Fisher bound. Any questions? Because now we're going to go on to quantum mechanics, which of course is where we want to be. All right. Oh God, look at that. Here's another case where it's going to appear that we have taken a detour that nobody but an idiot would take, but it's going to turn out to be useful in the end. And we'll get to that very much just in the center of our discussion. All right. So we've repeated here the quantum setting. Our total Hamiltonian is this, with little Hamiltonian h imposing the parameter gamma on the system. Here's the evolution of the system, and here's these equations that tell us how we get the probability of the estimator and from the POVM, and how we get how the Fisher is defined in terms of the probability of the estimator. All right. So now we just say, okay, we got this definition of the Fisher, and here's what this probability is in terms of the quantum mechanics, system state at time t, and POVM. And so we're just going to differentiate. So here's the point where we need to make a distinction, where we need to say why what we're doing is actually important. The evolution of the system is derivatives with respect to time. And what we're interested in is at a particular time t, how do these probabilities and all the other quantities change with the parameter, right? So the system state can be thought of as going on a little ride through system state space. And at every point, we're interested in how it changes if we change the parameters. the parameter gamma, okay? So there's two different kinds of derivatives. And you can see that if we left this guy out of the picture, everything would be a heck of a lot simpler, because derivatives with respect to time would effectively become the same as derivatives with respect to gamma. That is to say, the evolution would just be e to the gamma ht, and gamma t is the thing that appears everywhere. And derivatives with respect to gamma would be equivalent or nearly equivalent to derivatives with respect to time. So we've actually made the problem considerably harder at the expense, with the benefit of knowing that all of that other decoration we had initially, where the system can interact with other systems, and we can do feedback and control and so on, we're taking all that into account, and none of it is going to do the slightest bit of good. It does no good whatsoever, except in a practical sense. It will not change the fundamental bound. None of it. Okay? Very important. So that's why we're going to all this trouble. All right, so now what we do is we just proceed with the program. Here's our expression for the probability of the estimator given gamma in terms of some quantum quantities, and we're supposed to take this derivative. So we just take it and do that. And we look at that and say, oh God, what do I do with that derivative of rho with respect to gamma? Well, here's the first thing you do. You just define a thing called the symmetric logarithmic derivative L gamma, which is a Hermitian operator. And it's a logarithmic derivative because you can see if rho was e to the L, then the derivative would just bring down L's and put them on both sides. It's symmetric because we have both of these terms here, which allows us to make L a Hermitian operator. And all of that's crucial. It's all crucial for saturating the bound. If we used other logarithmic derivatives, right or left, we wouldn't be able to saturate the bound. All right. So that's one way to write things. And why in God's name did we do that? Well, it is because we can take this formula, plug this in, write this like this, and this over here gives you the reason why we can use this. And it turns out that that derivative that appears in there is the real part of the expectation value of E gamma times L gamma, E gamma S times L gamma. Very cute, and that's really the whole point. But we can also do something else with this. We can write this guy in terms of a certain generator that we define K gamma, which is take the derivative of U with respect to gamma. Remember, that's rho U, sorry, that's HU. And then we put this U gamma on the other side, and so there's the HU, and there's this quantity, and that's T times H bar. Sorry, T times a kind of average value of H over the time of the interaction. So, and then you just muck around a little bit, and you can see you can write this like this. So that kind of looks like a von Neumann equation. That is to say, the derivative of rho with respect to gamma is our generator commuting with rho, but we've referred it back to the initial time with these evolution operators. And there's also a genius in that, which we're going to kind of skip over. I'm just going to show you we could do it. It might be more natural to write this generator, which is the one that's in the original von Neumann order, but we use this one instead. And the reason is because we can derive this equation, and K gamma just looks like that. Okay, so now we're going to kind of forget about K gamma for a minute. So why did we introduce it? Well, because in the end, everything's going to be in terms of that generator. And let me just note that if the H tilde is 0, H bar is just equal to H. So K gamma is just T times the Hamiltonian, okay? So everything's a heck of a lot simpler in that case. All right, now God, look at this. But this is full of things with techniques in quantum information science that, by God, you really have to be aware that these things are available to you. I already talked about the square root stuff, and now we're going to see the square root stuff big time. And being able to do this and knowing when to do it, this is one of the most important things if you want to work in quantum information, in particular in quantum metrology, okay? So there we just repeat some things that we had from before. This derivative that we're going to stick into the Fisher is given by this real part of a trace. So the derivatives disappeared in favor of this symmetric logarithmic derivative. And now we square that. We square that, and that's just obviously the real part squared. Well, the real part squared is less than or equal to the real part squared plus the imaginary part squared, which is just the absolute value squared. So we write that. At this point, we're basically just wandering around trying to figure out what to do. So that seems like a good thing to do because this real part looks like a terrible nuisance. And now we make this wonderful step with all the square roots. So we divide this rho gamma into a square root times a square root, and we move one square root over on the left using the trace property. We divide E gamma S into 2 square roots, and there's our symmetric logarithmic derivative. Those of you who are really quick will notice that this is just the operator version of the square rooting that we did before with the classical Cramer-Rao bound. And now we use the Schwartz inequality again, but now in its operator form. That is, the absolute square of a trace is less than or equal to the trace of this guy squared. So we're dividing this into 2 parts. The trace of this guy squared, and that's just this, times the trace of this guy squared, and that's just this. And we simplify, and what does it come out? This is the probability for gamma S, and this is the trace of L gamma, rho gamma, L gamma, and F is less than or equal to, we got 2 inequalities here. And what did I tell you when we have inequalities? The first thing you should ask is, can you saturate those inequalities? So we're going to suspend that question, but that should be on the tip of your tongue now. Carl, are you going to show that this thing can be saturated? If you can't, then go away. I don't need to talk to you anymore because your bound may be a piece of total nonsense. You can always prove something's bigger than or equal to something that's so little that it's irrelevant, right? I can write down bounds all over the place that are completely useless, okay? All right. So what we end up with is that the classical Fisher is less than or equal to this. And anybody see what's going to happen there? Whoa, because of the completeness property of the POVM, this integral over gamma S, E gamma S is just going to be 1. So there's a 1 sitting there, and we just end up with this. We put the L gammas next to each other, and that's the quantum Fisher information, or the whole thing is the quantum Cramer-Rao bound. That is, the quantum Fisher information is just the second moment of this thing called the symmetric logarithmic derivative. And that's why the symmetric logarithmic derivative is important, okay? The quantum Fisher information is the expected value of its variation, it's a deviation from its mean, because its mean value is equal to 0, that's easy to show. And so the quantum Fisher information is the variance of some Hermitian operator. Now, God, isn't that amazing? Of course, you don't have a clue what any of this means at this point, but the people who first showed this in the quantum version were Hellstrom and later Holovo, and this was a real act of imagination for them to do, to realize that the symmetric logarithmic derivative is the right thing to use. Although they didn't actually show saturability. So even though they chose the right thing, they didn't take advantage of the fact to show saturability in their original work. All right. Now, something has, so we're just summarizing now. And this is the kind of thing that I just love, strings of inequalities. The deviation of our estimate of the parameter from the true value, that's its mean squared value is this. That's supposed to be greater than or equal to 1 over f of gamma plus delta gamma squared, greater than or equal to 1 over f of gamma, greater than or equal to 1 over q gamma, which is equal to this. And that's the whole quantum Fisher bound. Now, something has slipped away while we were doing this. And you will notice I said from the beginning that in quantum mechanics, this is going to be about distinguishing two density operators that are close to each other. And how do you do that? You make some measurement, convert the density operators into probabilities for those measurement results, and then basically use classical Fisher on that. But here, where's the measurement gone? There's no measurement anywhere, right? So where'd the measurement go? It's in those, yeah, where'd the measurement go? Yeah, well, that's the question. What happened to the POVM? Excellent. Yeah, absolutely. What happened to the blasted POVM? So this is kind of like a magician working, right? Oh, you're going to tell me what happened to the POVM. Sorry? The POVM disappeared here when I integrated it over all its possible values, and it's complete, so it's integrates to the identity and disappears from the description. But there has to be but then there has to be something about what kind of measurement actually does a good job, right? What kind of measurement does a good job? I mean, because clearly you could go in there and make a measurement. Actually, one possibility for the measurement is to measure the identity, which just says the system is there. Well, that would tell you nothing about the parameter, right? So there's got to be something that in this, the POVM disappeared. There could be something in it where we learn what POVM to use. And where could that possibly be? Well, it's hidden in these two inequalities. To saturate those, we'll have to pick a certain E gamma est in order to saturate those inequalities. And that will be the optimal measurement. Now, this is a thing that loads of people who work on Fisher information, well, they've never been through this proof, so they've forgotten that the whole point of saturating the bound is it tells you what the optimal measurement is. There's no "the" there. It tells you an optimal measurement. There may be many others. Because the one that it tells you is probably not one you'd ever want to go make, but could be. But there's certainly been loads of other optimal measurements you could make. And where does that appear in the thing? So this is where a theorist really gets excited. It appears in these two inequalities here, and now we got to ask what's necessary to saturate them. So I think that's the next slide. A bit of a problem here is that my laptop didn't go into presentation mode where the next slide is shown on the right, and I didn't put it there. So I don't have, oh, but it is the next slide. Okay, terrific. So there's our quantum Cramer-Rao bound, and now we have to ask, saturating the quantum Cramer-Rao bound requires using a measurement that saturates the two inequalities that separate F from gamma, and here is those two inequalities. One of them is actually that the trace of this quantity is real, doesn't have an imaginary part. And the second is that, oddly enough, this goofball quantity with square roots in it and the L gamma is proportional to this. So the L gamma is in the middle, And the L gamma doesn't make any difference in some sense because this is proportional to this. That's what we need to satisfy. Now, if you're not familiar with operators, or even if you are, this looks like a complete disaster. How in God's name are we ever going to get these two things to be true? And of course, the wonderful thing is, it's not a disaster at all. We just measure in the eigenbasis of L gamma. So L gamma is an operator, permission operator. It has an eigenbasis. There's its eigendecomposition. It has eigenvalues lambda j, which nicely go with L. And these are the projectors. These are the eigenstates of the symmetric logarithmic derivative. Now you say, God help me, I still don't have a clue what you're talking about. We will get to a point where we will tell you that all this mumbo jumbo has a very simple interpretation in the end. All right, so we're going to measure this POVM. These are projectors, so this is a von Neumann measurement. The E's are just equal to the projectors on the eigenstates of L gamma. And it's not hard to see that because E and L commute, these things are just trivially true. And here that just sort of goes through that. But because E and L commute, we can put E through here, rearrange the trace and show that this thing is real. And because E commutes with L, this can come over here. So then it looks like that, and the L only just changes, puts an eigenvalue in. Okay, so it all works. You measure the symmetric logarithmic derivative. Now, it is also true that it's up to you, the user, to figure out how to turn this result J into an estimate of the parameter. But, we have to leave something to the user. But that's the way it works. Okay, so that's a wonderful thing about the single parameter estimation bound. It automatically tells you a set of conditions for the optimal measurement, and those conditions can be satisfied and you can achieve the bound. For multi-parameter estimation, you'll get a similar set of conditions, but they can't be satisfied generally because there's a whole set of matrix conditions, and you can't satisfy the conditions generally. All right. Now, whoa, and here's where the rubber hits the road. Here's what we had before, and here's our L gamma. And now we're going to specialize to pure states. Now, the quantum Cramer-Rao bound applies whether you have pure states for your system or not, but it is saturated by having pure states. So the pure states, some pure state is the optimal state. And so we might as well just specialize to pure states. And then we use this wonderful property that for a pure state, rho gamma is square, to tell us that the symmetric logarithmic derivative is just twice this derivative. And that derivative, we already know what it is in terms of this mass here. And so to get Q, what do? We have to put the square of that in. So we square everything, screw around, put it all in there, simplify radically, blah, 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 blah. And out comes this, that the Fisher information, the quantum Fisher information for a pure state is 4 times the delta K gamma squared, the uncertainty in K gamma, and K gamma is just T times this average Hamiltonian. So it's 4T squared times delta H bar squared. And that's not H bar, it's delta average H squared. Okay. Now, if we don't have those control parameters, then U gamma is just given by this, as I said. K gamma is just TH. The average H is just H, and L gamma is just the commutator of H with rho gamma with some 2 T's thrown in. What about that 4 and the 2? That 4 and 2 are the same things that appear in the Robertson uncertainty principle when you have delta X squared, delta P squared greater than H bar squared over 4. It's the same 4. It appears here for the same reason. All right. Although you might not recognize that if somebody didn't just tell you, and you probably don't believe me. Anyway, now we're going to get to the point of actually figuring out what the optimal state looks like big time. So remember that we now have this string of inequalities, and we're going to write them upside down. 1 over the uncertainty in our estimate is less than or equal to the square root of the classical fissure, less than or equal to the square root of the quantum fissure, which is 2t times the uncertainty in this average h. And now we note the uncertainty in the average h is limited by the difference between the largest and smallest eigenvalues of h. Actually, in this case, h bar. And because the difference between, and we're calling that this norm, that obeys the triangle inequality, so that's less than or equal to t times the unaveraged h. Okay, so terrific, terrific, terrific. Now we're set. And what's the optimal state? The optimal state is the one that is a superposition of the largest and smallest eigenvalues. So there's the state of h that has the largest eigenvalue. There's one that has the smallest eigenvalue. Should be a parenthesis there. And there's what those things are. And the optimal state is this. So now we're cooking. We can tell you what all this actually means in the end. So this enormous apparatus, screwing around with equations, we're going to tell you what it actually means in the end, what the Fisher bound actually means. The Fisher bound is actually always about a qubit problem where there are only 2 states that are important. That is the whole blasted story with the Fisher bound. So all that immense apparatus mucking around, it comes down to the thing I'm going to show you now. All right. Oh, so yeah. There we're just repeating what we said before. We have this long string of inequalities, and we'd like to actually achieve that bound. And if we want to achieve that bound, we're going to need to leave out all the control mechanisms. We will do better by leaving them out. Now, it might be that the control mechanisms muck around with the system and keep it on track so it does a better job practically, but fundamentally, it is of no use whatsoever. You'd like to leave all that stuff out. So you might ask, why did I put it in? Well, it was so that I had a lecture with long enough to fill out the time. That's clearly the reason. Otherwise, I could have done this in 10 minutes. What? It can be any superposition that. Yeah, it could be, but it needs to be the one with equal weights on the highest and lowest. Yeah, but I'm just choosing that one. It's quite true. It can be any superposition that. So we could put a phase here, and it would still work. It'd be the same thing. Now, so what does all this mean? So the really crazy thing about the quantum Cramer-Rao bound is that to make the most sensitive measurement possible, you're told to make something as noisy as possible. That is to make h, the variable that imposes the parameter, as noisy as possible, okay? And the thing that a lot of people miss, because it's hard to find, what it whispers to you, and most people don't even hear the whisper, is that for pure states, there is a very quiet conjugate observable, the symmetric logarithmic derivative of L gamma, and you're instructed to measure that. And so now we're going to forget all of those control parameters, and here's the observable that you want to measure. And why is that the obvious observable to a measure? I'm about to show you. Because looking at that, you look at that and you think, oh God, help us. I don't know what to do with that. But here's what you do with it. So the whole thing reduces to a qubit problem. Here's what happens. So H has the following property: that the thing that imposes the parameter has the largest eigenvalue, eigenstate, the smallest one, and then all kinds of other stuff that turns out to be totally irrelevant. And one can write this as, if you're familiar with Bloch spherology, and I have to say, if you want to work in quantum information science and you're not totally familiar with Bloch spherology, well, you need to go become totally familiar with it, because it's a whole story in the end. Anyway, this thing is 1/2 the identity plus 1/2 the Pauli Z operator with these sums and differences appearing in front of the identity in Z, plus all the irrelevant orthogonal stuff. Okay, so what happens when we impose the parameter? Imposing the parameter means we evolve with this Hamiltonian, and that just puts phases in front of these two guys plus so we left out the all the irrelevant stuff, and this is just, we're going to call this the +1 eigenstate of a rotated X, rotated by this, rotated Pauli X, rotated by this from the standard X by this rotation. And now, what are you supposed to measure? Oh, that's just writing that stuff out. What are you supposed to measure? The symmetric logarithmic derivative, which turns out to be the same thing, essentially, with a minus sign here, which means it's measuring the Pauli Y. So what you're instructed to measure is, let's see, there's a blackboard here. I should have drawn a picture of this, but. So the fiducial state, so the beginning state, let's say, is here, but it's rotated by that e to the minus iht to sit over here. And now you're going to look, so this is what we're calling the Pauli X, this direction. And the measure, you're looking for little changes along the equator. And so you should measure the orthogonal Pauli operator, which is the Pauli Y operator. And that's what the whole thing tells you in the end. So the whole thing in the end comes down to just that. On a Bloch sphere, you start here, you have a little rotation that you want to detect. And so you measure the orthogonal Bloch sphere component. And that's the whole story. It's a whole story with quantum Fisher information with the optimal state and the optimal measurement. All right. I'm sure you're tired, and I'm incredibly tired, partly because I didn't sleep for 5 minutes last night. And that's because North America is somewhat regrettably 12 hours away. And it's hard to go to sleep in the middle of the night. All right, thank you.
Questions? There is one. Yeah, go ahead.
Yeah, so your point with what happened with POVM, I didn't get that. You said that there is a choice of projective measurement in one of the slides. So what actually was your point in saying that the measurement goes away?
What was my point in doing what?
The measurement went away at the end of when you derived this Cramer-Rao bound for quantum Fisher information, right?
I'm still not getting the question. Somebody can help me.
POVM went off.
Oh, you mean how did the POVM disappear?
No, I understood mathematically, but you had some point saying that what happened to measurement.
Yeah.
yeah.
So
So
the
could you
POVM
repeat that?
disappeared. The POVM disappeared, but there were two conditions necessary to satisfy the inequality, and that specified the POVM that does the best job. And the POVM that does the best job is actually a projection valued POVM. So I didn't actually need POVMs. I just needed von Neumann measurements. But if you're going to prove something in quantum mechanics, you have to allow for all possible measurements, and then it might turn out that the best measurement is a projection valued measurement. And here it is. Now, in practice, it's often true. So there's two things I should say about in practice. In practice, I have assumed finite dimensional Hilbert spaces, and the quantum Cramer-Rao bound will often not fail, but be hard to interpret in infinite dimensional Hilbert spaces. So if I was doing an interferometer, like I did yesterday, I would do an interferometer with a fixed number of photons in it, and then all of this would work. If I did an interferometer with coherent states, I'd have to think a little bit before I would use the quantum Cramer-Rao bound. And so that means that my optimal measure, oh, and then the second point is that even in the finite dimensional Hilbert spaces I'm talking about, it could be true that there are other measurements that work just as well as the one we just talked about. And in particular, in a high angular momentum system, you could just measure the orthogonal components of angular momentum and not worry just about the highest and lowest eigenvalues. You could just do that. The other things won't occur. They just, well, nothing will happen with them.
I too like to get rid of the feedback loops, but I wonder what you're saying is for a linear feedback only, or you're saying that even with the
anything. Anything. It doesn't in principle, it doesn't make anything better in principle. It could be that the whole thing will go on. It could be that there are other Hamiltonians than that one that imposes the parameter, which will make the thing go nuts. And then you need some feedback to keep it under control. But in principle, the feedback doesn't do any good at all.
even not.
I mean, this assumes you stay at the lock point, right? It assumes there's nothing that knocks you away from the lock point. And if there was something that knocked you away from the lock point, you'd need feedback to move you back there, okay?
But something that changes the dynamics of the system with the nonlinear feedback, that still doesn't improve measurement accuracy.
So what the proof actually says, if there was stuff that knocked you out of lock or screwed around with the system, you should get rid of that. And the way you get rid of it could be with feedback, but the proof just says that doesn't help, so get rid of it. So it's not a very good instruction for an experimenter. It's basically, you got problems, get rid of them. It's not the statement that the problems are going to go away on their own.
Sai?
Yeah, hi, Carl. So just two quick questions. One is, so you were emphasizing this symmetric logarithmic derivative as kind of the thing that saturates, right? And so I understand, I guess, mathematically how it comes up, that you've taken a parametric derivative, and now in classical probability distribution, there's no problem of commutativity, but in quantum, there is this issue that you operator ordering. And
So
that's
you're talking about multi-parameter? Or
no, just even single parameter,
this.
why you would want to introduce both the left and the right, the symmetric logarithmic. And now I can see mathematically why it saturates, but I was wondering if you had any deep intuition as to why it saturates, or to ask the question differently, why is it that when the right right logarithmic derivative or the left order logarithmic derivative are discussed, that they don't necessarily saturate? Like, what's the...
Yeah, they're generally not going to be Hermitian.
Yes.
And so they will have other parts that
Complex
contribute
parts.
to the noise and are not, certainly not.
Oh,
optimal.
okay. So I should interpret the complex piece as noise that basically takes me away from the optimal. Okay.
So I think it all has to do with that. I mean, I haven't actually done this forever, so I'm riffing. well, the whole thing was a riff, but I actually knew what I was talking about. Here I don't know what I'm talking about. I think it all has to do with that real condition, that you're going to have a
Yes, yes.
real hard time with that if you have right or left.
I can check.
derivatives.
Actually. Yeah. Okay. Thanks. And the
This
second.
is not to say they're useless. For some problems,
Yes.
you can just see in advance that they do the job
Yes.
and you just use them.
And the second very quick question that I had, again, as a follow-up of this, feedback does nothing. I think it just, so whenever I have this H of H tilde of T in your Hamiltonian, right? I could interpret it as a term that pumps energy into the system, right? And so to me, if I start with pure states, kind of the folklore is 4 times the variance of the Hamiltonian. And I'm just a little bit surprised again that even though I'm pumping energy into the Hamiltonian, which means in principle, it's, I could be increasing its energy, that's not contributing in any way towards improving the accuracy.
Yeah, and I think that has to do with the restriction I've had of working in finite dimensional Hilbert spaces. That
okay.
is to say, there really isn't any notion of pumping energy into the system. Now, if your preparation didn't put you in this correct state, well, then certainly you'd love to have some feedback that took you from what the crummy state you started with to the optimal state. Or as I was saying to Rana, if there are other pieces of the Hamiltonian that knock you away from the optimal state, then you'd want to put some feedback that restores it and get back to lock point. But all that's just a statement that you want to work with the pure Hamiltonian that's gamma H. And if you have things that take you away from that, then fix them. But it would be better if you didn't have anything that screwed you up to start with. I mean, you'll never do better than just working with that Hamiltonian.
Are there any query from the student side? Okay, if not, then Saikat goes first.
Yeah, this is regarding towards the end, the statement you made that to choose the generator such that it's as noisy as possible, just corresponding to the state. Can you give some intuition on that, particularly in the context of the diagram you drew here?
Sorry, could I talk about?
The generator, you were saying that it should be chosen in a way to have it as noisy as possible, like to make the system as noisy as possible for the parameter estimation, right?
Yeah, the generator, the H is handed to you. The little H is handed to you. There's nothing you can do about that.
And when you say noisy, what do you mean by that? Like
What do you mean by
by choosing it such that the system is as noisy? Particularly in this diagram, how would I understand it?
Not quite sure what the question is.
Maybe you can repeat the question once.
It's regarding the statement you had in the previous slide. It's just kind of just the earlier slide. Corresponding.
Oh, yeah. That's the statement. That's the statement that we're referring to. Sorry.
And that's
what the Cramer-Rao bound says is you should make H as noisy as possible. That is, give it as big an uncertainty as possible. And so this is kind of like squeezing. Well, it actually is identical to squeezing. To do well with measuring one thing, you make the conjugate observable as noisy as possible. And this is just a very general statement of that. It is, however, in typical. So it's important to realize we're dealing with pure states, because you can make something incredibly noisy in a mixed state and not make the conjugate observable have small uncertainty. But in a pure state, there's some uncertainty principle underlying the whole thing, which says make H as noisy as possible. And then there's this conjugate observable L gamma, which will be as little noisy as possible. And that's the thing you should measure. And it is the thing that responds directly to the parameter, sees the parameter as best as possible. So it's, I just find that most people, when they talk about Fisher information, have totally missed this point. And so They think, oh, there's a heck of a lot of information in there because H has the biggest uncertainty you can imagine. But that's really not the point. The point is there is a conjugate observable hidden in the proof that will have, in the optimal state, very little noise. And that's why you can do a good job.
Saikat, go ahead.
Sorry. So my question has to do with your the statement about the optimal state. Is there a equivalent or generalization of a statement like that for infinite dimensional Hilbert spaces with say a mean energy constraint of the input state?
Yeah, obviously, if you tend to have energy constraints, then you actually end up in a finite dimensional Hilbert space, and all this matters. If you have average energy constraints,
Average energy is what I meant.
then
Yes.
you often run into problems trying to apply this, and those problems you have to deal with, as far as I can tell, on a sort of case-by-case basis. I mean, it's often true that, the optimal state for measuring the phase of a single mode is a superposition of vacuum and a state with
Largest
a
one.
hell of a lot of energy in it.
Exactly.
That has a very small amplitude, and you detect things by finding yourself very rarely having started in that state with a lot of energy. And so, I mean, there's all sorts of questions that, Mankey has addressed in the case of average energy, that they sort of slip through the proof, and it makes you think you can do something extremely well, but in practice you can't.
So
And I can't make a very good statement
Yeah,
about that, Saikat,
that's
because
interesting,
I've,
Carl. I mean,
uh,
I was wondering if there is so as you mentioned on the measurement side, there is a degeneracy. The SLD eigenvectors are only one measurement. In fact, there is a nice constructive way to think of how you can come up with an infinite family of optimal measurements. I'm wondering, for the infinite dimensional case, is there a similar degeneracy one could make a nice statement about? Like, for example, as you said, if you put a fixed photon constraint, the noon state is the best one. On the other hand, as you pointed out, squeeze states, and there's this fixed photon number, split states. So all these states that all achieve the Cramer-Rao bound for phase dimension. So for a mean energy constraint, is there a nice way to formulate a statement like that?
I do not know of one. Sometimes when you have mean energy constraints, the quantum Cramer-Rao bound makes perfectly sensible bounds that obviously are the right answer. But there are certainly problems you can dream up where it doesn't. And then those kind of have to be dealt with on a case-by-case basis. And I'm not aware of any general statement one can make.
Okay, any other questions? Okay, there is a question. Thanks.
Hello.
Oh, I thought I was relieved of duty, but I guess not.
So you have told that H tilde cannot see the parameter gamma, right?
Is it one?
H tilde cannot see the parameter gamma. Cannot see the parameter gamma. So your total Hamiltonian was two parts, has two parts actually. And the later part, H tilde cannot see the parameter. Your parameter, right?
Yeah, it's kind of just a statement that the Hamiltonian divides into two parts, the part that sees the parameter and the part that doesn't. And it is true, one has assumed that the part that sees the parameter is linear in the parameter, but otherwise there's really no assumption there. There is a part that sees the parameter, linear in the parameter, plus everything else that could involve other systems. And none of that will change the bound. None of the H tilde will change the fundamental bound.
I mean, this also implies that any correlation in your surrounding is quickly lost, or that kind of thing also.
I didn't quite get that.
I mean, I want to know, is there like Markovian approximation in your whole derivation?
Does somebody want to?
So is there a some sort of a Markovian approximation in your overall derivation? I don't know what you mean
No,
by
I
that.
don't think it has anything to do with Markovian. Because I evolve, you just evolve for a certain amount. No, I'm pretty sure it has nothing to do with Markovian. Absolutely sure.
Thank you.
Okay, so if there are no further questions, then let us thank Professor Carl Gibbs, and I request Kasturi to give a small memento on behalf of the organizer.